Welcome to CSEGuru. In this session, we are going to discuss one more example to implement Floyd Warshall's algorithm. So the Floyd's algorithm is nothing but it is used to find all pair shortest path problem. That is, what is the shortest path from each vertex to all other vertices in the given graph. That is, shortest distance from 1 to 2, 1 to 3, 1 to 4. Then 2 to 1, 2 to 3, 2 to 4. Then 3 to 1, 3 to 2, 3 to 4. Similarly, 4 to 1, 4 to 2, 4 to 3. What is the shortest path? That is from every vertex to all other vertices. It is used to find the shortest path. So the Floyd's algorithm is commonly called all pair shortest path problem. Already we have discussed one example to implement Floyd's algorithm. I will provide the link in the description for your reference. So this is the given graph. For this graph, we need to find the shortest path between every pair of vertices. So the first step if you are considering, we need to find the cost matrix. So in this given graph, they have given the directions. So we need to consider the direction to enter the cost into this cost matrix. And one more thing we need to remember, we are not going to find the shortest path from the vertex to itself. It is not necessary. So the cycle values, that is 1 to 1, 2 to 2, 3 to 3, the values always it will be 0 only. And if you are considering 1 to 2, the distance is 3. There is a directed path and its distance is 3. And 1 to 3 if you are considering, there is no directed path. We don't know the distance. So we need to consider it as infinite. And 1 to 4 distance is 5. Then 2 to 1, the distance is 2. There is a directed path. And 2 to 3, there is no directed path. We don't know the distance. So it is infinite. And 2 to 4, there is a directed path. Its distance is 4. Similarly, 3 to 1, there is no directed path. We don't know the distance. So it's infinite. And 3 to 2, its distance is 1. And 3 to 4, there is no directed path. We don't know the distance. So it is infinite. And 4 to 1, there is no directed path. It's infinite. 4 to 2 also there is no directed path. Infinite. And 4 to 3, there is a directed path. Its distance is 2. So this is the cost matrix. With the help of the cost matrix, we are going to implement step by step by considering the shortest path through every vertex. That is 1, 2, 3, 4. Likewise, in each step, one vertex we will consider it as an intermediate vertex. And through this vertex, whether there is a possibility of shortest path or not, we are going to find. Step 1. Consider the shortest path through vertex 1. That is the first vertex we are going to consider as an intermediate vertex. And through this vertex, what is the shortest path? We will find out and fill the matrix. Since we are considering the intermediate vertex as the first vertex, we are not going to disturb the first vertex column values and row values. As it is, we need to keep. And the new matrix, what we are going to find is R of 1. Initial cost matrix, we need to consider it as R of 0. And the new matrix, what we are going to find is R of 1. Since we are not disturbing the row values and column values of first vertex, the values we need to consider as it is. And the remaining positions, we are going to find the values. Similarly, the diagonal values, we are not going to find. The values will be always 0 only. So next we need to find 2 to 3. So 2 to 3, what is the shortest path? We need to find. So the formula is, we need to consider minimum of the directed path 2 to 3 or through this intermediate vertex. That is 2 to 1 plus 1 to 3. So in between we have inserted this intermediate vertex 1. So through this vertex, whether there is a possibility of shortest path or not. So 2 to 3, already the value is infinite in cost matrix. That is the initial matrix. Already the value is infinite. And 2 to 1, if you are considering, the value is 2. Plus 1 to 3, the value is infinite. So we will get infinite only. So this position is infinite only. Next is 2 to 4. So minimum of 2 to 4, comma, through the vertex 1. That is 2 to 1 plus 1 to 4. So 2 to 4, if we are considering, already the distance is 4. And 2 to 1, the distance is 2. Plus 1 to 4, the distance is 5. So this is 4 and this is 7. So minimum is 4. Next is 3 to 2. Minimum of 3 to 2, comma, through the vertex 1. So 3 to 1 plus 1 to 2. So we will get it as 3 to 2, the distance is already 1. And 3 to 1, if we are considering, the distance is infinite, plus 1 to 2, the distance is 3. So the minimum value is 1 only. Next is 3 to 4. And 3 to 4, if we are considering, minimum of 3 to 4, comma, through the vertex 1. So 3 to 1 plus 1 to 4. So we will get it as 3 to 4, already the value is infinite. And 3 to 1 is also infinite, plus 1 to 4, the distance is 5. So which one is minimum? Infinite only. And 4 to 2. So 4 to 2, if you are considering, that is minimum of 4 to 2, comma, through the vertex 1. So 4 to 1 plus 1 to 2. 4 to 2, the distance is already infinite. And 4 to 1 also infinite, plus 1 to 2, if you are considering, the distance is 3. So we will get it as infinite only. So the values, if you are considering, this is 1 and this is infinite and this is also infinite. Now we need to find 4 to 3. So minimum of 4 to 3, comma, 4 to 1 plus 1 to 3. Through the vertex 1 we need to consider. So 4 to 3, the distance is already 2. And 4 to 1, it is infinite. 1 to 3 also infinite. So we will get it as 2 only. This value is infinite. Next is step 2. Consider the shortest path through the vertex 2. So here we need to consider the matrix R of 1. So this is the new matrix we have found out in step 1. Since we are considering the intermediate vertex as vertex 2, we should not disturb the row values and column values of vertex 2. And the remaining positions we need to find. And the new matrix what we are going to find is R of 2. So the row values and column values of vertex 2 as it is we need to write. We should not disturb the values. And the remaining positions we need to find. And here diagonal values, always the values will be 0 only. So the remaining positions if we are considering, there is 1, 2, 3 we need to find. So 1, 2, 3, minimum of 1, 2, 3, comma, through the vertex 2. So in between we need to insert the vertex 2. So 1 to 2 plus 2 to 3. What is the shortest path? So 1 to 3, if you are considering, the distance is already infinite. And 1 to 2, it is 3 plus 2 to 3, it is infinite. So we will get it as infinite only. Next, 1 to 4. Minimum of 1 to 4 through the vertex 2. So 1 to 2 plus 2 to 4. So 1 to 4, if you are considering, already the distance is 5. Comma 1 to 2, it is 3 plus 2 to 4. Distance is 4. So which one is minimum? 5 is minimum. So the value is 5 only. Next 3 to 1. Minimum of 3 to 1, comma, through the vertex 2. So, 3 to 2 plus 2 to 1. Here, just we need to insert the vertex 2 and we need to add the cost. 3 to 1, already the distance is infinite. 3 to 2, distance is 1 plus 2 to 1, distance is 2. So, we will get it as 3. Next, we need to find 3 to 4. Minimum of 3 to 4 through the vertex 2. So, 3 to 2 plus 2 to 4. So, 3 to 4, already the distance is infinite, comma, 3 to 2. it's 1 and 2 to 4 it is 4. So 1 plus 4. So the distance we will get it as 5. Next is 4 to 1. Minimum of 4 to 1 through the vertex 2. So 4 to 2 plus 2 to 1. So 4 to 1 already the value is infinite. 4 to 2 also infinite plus 2 to 1 the value is 2. So we will get it as infinite only. Next is 4 to 3. So minimum of 4 to 3 through the vertex 2. So 4 to 2 plus 2 to 3. So 4 to 3 already the value is 2. And 4 to 2 plus 2 to 3. 4 to 2 it is infinite. 2 to 3 it is also infinite. So the distance we will get it as 2 only. So this is the new matrix we have found out by considering the intermediate vertex 2. And the new matrix is R of 2. Next, step 3. Consider the shortest path through the vertex 3. So the intermediate vertex we need to consider as vertex 3 and we need to find the shortest path. Since we are considering the intermediate vertex as 3, we should not disturb the third vertex row values and column values as it is we need to keep. And the new matrix what we are going to find is R of 3. So keep the values of vertex 3 as it is. And also the diagonal values will be 0 only. And the remaining positions we need to find the shortest path by considering the intermediate vertex 3. So 1 to 2 we need to find. Minimum of 1 to 2, comma, through the vertex 3. So 1 to 3 plus 3 to 2. So already 1 to 2 the distance is 3. 1 to 3 is infinite plus 3 to 2 is 1. So we will get it as 3 only. Next 1 to 4. Minimum of 1 to 4 through the vertex 3. So 1 to 3 plus 3 to 4. So 1 to 4 already distance is 5. 1 to 3 distance is infinite plus 3 to 4 it is 5. So we will get it as 5 only. Next 2 to 1. Minimum of 2 to 1 through the vertex 3. So 2 to 3 plus 3 to 1. So 2 to 1 the value is 2 and 2 to 3 it is infinite plus 3 to 1 the value is 3. So we will get it as 2 only. Next 2 to 4 we need to find. Minimum of 2 to 4 comma intermediate path is 3 vertex 3. So 2 to 3 plus 3 to 4. So 2 to 4 the distance is already 4 and 2 to 3 is infinite plus 3 to 4 is 5. So we will get it as 4 only. Next is 4 to 1 and 4 to 2. So 4 to 1, minimum of 4 to 1, comma, through the vertex 3. So 4 to 3 plus 3 to 1. So we will get it as a minimum of 4 to 1. 4 to 1 already the value is infinite. And 4 to 3 it is 2 plus 3 to 1 it is 3. So we will get it as 5. So the shortest distance from 4 to 1 is 5. Next to 4 to 2, minimum of 4 to 2, comma, through the vertex 3. So 4 to 3 plus 3 to 2. So 4 to 2 already the value is infinite. And 4 to 3 if you are considering value is 2 plus 3 to 2 value is 1. So the shortest distance we will get it as 3. So R of 3 is the new matrix we have found out by considering the intermediate vertex 3. Next is step 4. Consider the shortest path through the vertex 4. So the intermediate vertex we need to consider as vertex 4. Since we are considering the intermediate vertex as vertex 4, we should not disturb the row values and column values of vertex 4. And the remaining values we need to find. And the new matrix what we are going to find is R of 4. So the row values and column values of vertex 4 as it is we need to write. And also the diagonal values will be 0 only. So we need to find the shortest path for 1 to 2, 1 to 3. So 1 to 2 if you are considering minimum of 1 to 2, comma, through the vertex 4. So 1 to 4 plus 4 to 2. In between, we need to insert vertex 4. So 1 to 2, if you are considering, already the distance is 3. And 1 to 4, it is 5. Plus 4 to 2, it is 3. So which one is minimum? 3 is minimum. Next is 1 to 3. Minimum of 1 to 3, comma, through the vertex 4. So 1 to 4 plus 4 to 3. So 1 to 3, already the distance is infinite. And 1 to 4, if you are considering, it is 5. Plus 4 to 3, it is 2. So we will get it as 7. So the shortest distance from 1 to 3 is 7. Next, 2 to 1 and 2 to 3. So minimum of 2 to 1, comma, through the vertex 4. That is 2 to 4 plus 4 to 1. So 2 to 1, the shortest distance is already 2. And 2 to 4 is 4. 4 to 1 is 5. So which one is minimum? 2 is minimum. Next is 2 to 3. Minimum of 2 to 3, comma, through the vertex 4. So 2 to 4 plus 4 to 3. So 2 to 3, it is already infinite. 2 to 4 is 4 plus 4 to 3 is 2. So the distance is 6. Next is 3 to 1 and 3 to 2. So 3 to 1 is minimum of 3 to 1 through the vertex 4. So 3 to 4 plus 4 to 1. So 3 to 1, already the distance is 3. And 3 to 4, the distance is 5. Plus 4 to 1 is also 5. So we will get it as the minimum value is 3 only. Next, 3 to 2. Minimum of 3 to 2, comma, through the vertex 4. So 3 to 4 plus 4 to 2. So 3 to 2, already the distance is 1. 3 to 4, it is 5. Plus 4 to 2, the distance is 3. So we will get it as the minimum value 1 only. So this is the new matrix we have found out by considering the intermediate vertex 4. So now if we are considering, we have considered all the vertex as the intermediate vertex in each step, and we have found out the shortest path. So this is the final matrix which gives the shortest path from each vertex to all other vertices. So this is nothing but the Floyd's algorithm. So shortest path from 1 to 2, it is 3. And 1 to 3, if we are considering, there is no direct path. Through the vertex 4, we need to consider. So 1 to 4 and 4 to 3, distance is 7. And 1 to 4, if we are considering, there is a directed path and its distance is 5. This is minimum. And 2 to 1, there is a directed path and its distance is 2. And 2 to 3, this direction is wrong. This is the direction. And 2 to 3, if you are considering, there is no directed path. We need to consider the path through vertex 4. So 2 to 4 and 4 to 3. The distance is 6. And 2 to 4, if you are considering, it is a directed path. Distance is 4. Similarly, 3 to 1, there is no directed path. So we need to consider the shortest path through the vertex 2. So 3 to 2, 2 to 1. Distance is 3. And 3 to 2, distance is 1. 3 to 4, there is no directed path. We need to consider through the intermediate vertex 2. So 3 to 2, 2 to 4. Distance is 5. Similarly, 4 to 1, distance, there is no directed path. So we need to consider 4 to 3, 3 to 2 and 2 to 1. 2 plus 1 plus 2, it is 5. And 4 to 2, there is no directed path. We need to consider through vertex 3. So distance is 2 plus 1, it is 3. And 4 to 3, if you are considering, there is a directed path, its distance is 2. So this is the shortest path from each vertex to all other vertices. So the common name for Floyd's algorithm is all-path shortest path problem. And this is the procedure to implement Floyd's algorithm. In the next session, we are going to discuss the time complexity to implement Floyd's algorithm. Thank you for watching this video.